So let's have a look. Repeat the process for option 2. Okay, the mean is still 15 millimeters. The standard deviation this time is 0.075. Okay, the lower limit stays the same, 14.82 millimeters, and the higher limit has to be 15.18, exactly the same. So again, we follow the same procedure. We find the Z value of the lower limit, okay, the lower being 14.82, take away the 15, and then divide your answer by 0.075. And when you do that, you end up then with a Z score of minus 2.4. We then do the same for the higher limit, which is 15.18. Take away the 15, divide by 0.075, and we get a Z score for the higher value of 2.4. You may have noticed that the Z scores are actually the same, except for one is negative and one is positive. That's because, if you notice, our tolerances are actually the same. What is it? Is it 0.18 millimeters either side of the mean of 15? So they are symmetrical, so that does make sense that we are going to end up with the same Z value scores, but one will be negative and one will be positive. Okay, we then use the Z tables and we subtract the lower probability from the higher probability to find the probability that the unit is good, falls within the good range. Okay, so when you do that, you find the probabilities of the higher is 0.9918 and the probability of the lower value is 0.0082. Subtract lower from higher and you get a probability that the unit is good as being 0.9836 or 98.36% of components will be good. We're only interested in the defective ones because each defective component costs us £1. So we subtract this value from 1 and 1 take away 0.9836, 0.9836 gives us 0.0164. Well, that's a probability that a component's been defective. So now we multiply it by the number of units that we're actually manufacturing, which is 20,000. So 0.0164 times 20,000 tells us with this standard deviation, we're going to end up with 320 defective units. Notice last time we had 52 defective units because the standard deviation was tighter. It was a better standard deviation. Okay, so the setup cost is lower this time, £550, but we're going to have 320 defective units costing £1 per unit. Add these two together and we find out that option B will cost us £878. Of course, we've got 3 options, so we have to repeat exactly the same process for option 3. Okay, by now you could probably do this with your eyes shut. So repeat the process for option 3. The mean is still 15, but the standard deviation this time is 0.09 millimeters. Okay. The lower limit is 14.82 millimeters, just as before. The higher limit is still 15.18 millimeters. So we find the Z score for the lower limit. Remember, lower limit 14.82. Take away the mean, so take away 15. Divide it by the standard deviation, which is 0.09, and you're left with a value of -2. Z score of -2. For the higher, okay, we look for the higher limit, subtract the mean, divide it by the standard deviation, and we find, no surprise again, because as I said earlier on, it's symmetrical. We've got -2 for the lower limit, +2 for the higher limit. Using your Z tables, you can then convert those into probabilities, -2 and 2 into probabilities. And by subtracting the lower probability from the higher, what you have then is the probability that you are going to have units falling within the good range. Okay, let's do that. Whoops, jumping the gun there. Okay, so let's do it. when you look up those Z values of 2 and minus 2, well, the Z value of 2 will give you 0.9772. Okay, that's your probability, 97.72%, that it will fall to the left of the higher limit. Subtract the probability that it will fall within the area to the left of the lower limit, which is 0.0228. Subtract the lower from the higher, and you get a probability that you're going to get a good unit of 0.9544. Okay, 95.44% of those units will be good. Subtract this from 100%, or 1 take away 0.9544 will tell you that the probability of having a faulty unit is 0.0456, or 4.56%. Okay. Again, we're doing a run of 20,000 units and multiply it by 20,000, and we find out that we're going to get 912 faulty units. Again, you would expect more because of the change in the standard deviation. Okay, we're not being as we're not setting the machine up to be as accurate. Okay, hence why it costs less money to set up. Okay, so if we have a look at the actual cost for option 3, there's £100 set up. We get 912 units that are faulty, so that's £912. So the total cost, add them together, £1,012. So in answer to the question of which option, A, B or C, is the most cost effective, the cost of option 1 was £902. The cost of option 2, okay, we're going to get more faulty units, but set off against the cost of setting the machine up, we actually find that option 2 only costs £878. Okay, and finally option 3, we find that the cost would be £1,012. So in other words, which option would be the best, the most cost effective? The answer is option 2. The second option would be most cost effective. Okay, I hope this made sense. If not, watch it again, have a look at your Z tables, work through it, pause, do what you like, and hopefully ask me any questions.